Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. At yesterday's stream, I did the math for our projection matrix's handling of the near and far clip planes, but I forgot about the divide by z when I did it, and then we had to really quickly redo it. When somebody asked a question, actually, Sherlock asked a question, and it was like, so it's non-linear, and then I was like, no, so it's linear, and I was like, no, it's not, and I was like, oh, wait, I forgot about the divide by z, that's bad. And then we resolved it really quickly, but we didn't have a chance to get it working, so I gotta go in there, and I gotta actually finish making it work with the correct way of understanding, or the correct expectation of what OpenGL is going to do with that matrix once it gets its hands on it. Whereas right now, yeah, well, I guess, or before we did this, we had sort of forgotten the fact that OpenGL was going to want to divide. All right. I guess now that I look at it, this is probably Kim Jorgensen right in the chat was saying, hey, the near clip plane is set to a negative number. Is that a bug? It is. I don't know when that happened. It may be that that's our only bug. I don't know, actually. That certainly could be the fact. We may have other bugs. We kind of have to take a look at the routines here to see what's going on. So let's go ahead and do that. Yeah. Let's go ahead and just see what happens with that. It may be that we're working okay, but we got to test we also have to test this routine. I feel like I would feel more comfortable. In fact, you know what? I can do that right now. I'd like to be able to push some points through it and just see how they come out. So, for example, just make a test result here where I can multiply a vector times the matrix and see what the result is that comes out. So, for example, maybe I can put in the near clip plane, and then I can put in the far clip plane, and verify that those two things come out to be what we want them to be, which is to say they should come out with the W component and the W component and the Z components being equal to, the Z component being equal to negative the W component and positive the W component, respectively. I guess the only question is, we can't see in that multiplication what happens to the W coordinate in any real way because we don't actually return the W coordinate. So it's a little hard to say, but we can assume that the W coordinate is pretty clear what it would be because it's only a -1 there that's going to be affecting it. So we can assume that it's just the input Z. It's just it's just negative n. I'm sorry, it's just n, negative n, and negative f, right? Because it's the only thing that comes in. So we kind of want to see if when we put these things in, we get those values. Let's find out. Okay. And thinking it through too, yeah, well, I won't say anything further. Let's just take a look. So in our math routines, where are our math routines? I guess they're not loaded for some reason. That's all right. We'll just set a breakpoint there manually by the function name. So going in here, here's us creating the matrix. And let's take a look at what we get when we do these test multiplications. So here's test 0, here's test 1, and let's see what's coming out of those. So in this case, test 0 is coming out to be -1, and test 1 is coming out to be -3. Those are not useful values at all. So it looks like that does not seem correct to me at all, because we're passing in an n and an f there where it feels like those should be coming out much more sanely, right? Because first of all, one of them should be positive and one of them should be negative, as just a a start, right? Because we know that the near clip plane and the far clip plane are supposed to map to opposite sides, right? They're supposed to map to -1 and 1. And so the fact that these two values are coming out, are coming out with the same sign is not good, because the sign of the W coordinate in both cases is negative. What that means is then when this divides, right, when we get Z and W dividing each other here, we're going to get correctly, in this case, we're going to get 1. I'm sorry, incorrectly in this case, we're going to get 1. So we've got the right magnitude but the wrong sign. So this Z value should have been positive. When we do this one, -3 over -3, that one will give us the right result, which is 1. So it's possible that we got a correct equation for our Z for the far clip plane, but it doesn't look like we got the correct equation here for the near clip plane, because something about the way that we did it, we missed a sign somewhere, as I'm often want to do when I'm working through math. This is in fact why I've always wanted a good computer algebra system, because most of the time the reason I don't do more math all the time is just because it's so frustrating to try and make sure you don't make a mistake somewhere, and these are mistakes that a computer wouldn't make. But anyway, so here we go. Let's take a look at what's going on here and just make sure we've got things relatively sane. What I did was I said that here is the value that we're looking at, right, AZ plus B. And we know that it's going to get divided by -Z at the end of it, because that's what we're putting into the W coordinate. So we know that we want f of -n to equal -1 and f of -f to equal 1 when whatever we set these two things to. And so then we tried to do sort of a solve for what f of z would be, assuming that we're going to pre-divide through by -z, right? So if we pre-divide through by -z, the z's cancel, and here we're just left with a -a, and then here we're left with a -b over z. So that does look like the correct equation to me. As far as I can tell, that seems like a reasonable simplification of this. I don't see any error in that, unless I'm missing something about the way this is working, but I'm pretty sure that that is how OpenGL will do it. It will divide by z. I don't think it will divide by -z. So it's going to divide by, I'm sorry, it will divide by -z. I don't think it's going to divide by z, because it will divide by w, not -w. And we're putting -z into the W coordinate. So then we came down here to solve it. We said f of -n equals -1, and so the -1 is the result. That's what the function evaluates to. The -n is the parameter, which goes in the place of the z. We end up with -a, because that term is untouched. We end up with positive b over n, because the -n cancels the negative here, right? So then we solve for a. We essentially move -a to this side, which becomes a, and -1 to the other side, which becomes 1. And we have a equals 1 plus bn. And that is the term that we use to substitute back in to the existing equation. Again, did not see a bug there. Doesn't mean there isn't one. I just didn't see it. So then we come over here and we get the same kind of thing, but for b. So we have a negative f, I'm sorry, not for b, I shouldn't say, but for, we're using this equation. We have the same equation. We have a 1, that's what it equals. We have the -a, because that term is untouched from here. And then we have a positive b over f, because the negative b over z, when we plug in -f, the negatives cancel, and we just get the b over f. Solving that equation, we have to go ahead and substitute in the -a term here for what we actually solve for. We solve for a equals 1 plus b over n. So we have -1 plus b over n, and we retain the plus b over f term. We then distributed the negative to get -1, negative b over n, plus b over f, like so. And then we transferred the -1 to the other side, giving us a 2. We then had negative b over n and b over f, right? So b over f comes here, b over n comes here, so it's one minus the other. And then we cross-multiplied to make the denominator be the same, to make the denominator be nf, right? Or fn. So the b term here picks up a n, the b term here picks up an f, and that is correct. It is the bn, right? Because bf is the negative term, and bn is the positive term. So that leaves us with a bn minus f over f times n equals 2, right? At that point, we need to divide through to solve for b. We end up with 2fn, because that comes out to the numerator. N minus f goes to the denominator. And we end up with b equals 2fn over n minus f. Again, that looks pretty solid to me. I don't see the bug there. And if I don't see the bug there, I'm not going to see any bugs here probably, because this and this work together. So it would probably be very difficult to have a sign bug only in this one. But I guess you never know. So we'll keep going. So there's our 2fn over n minus f. We then have to plug that in, right, to the b to solve for a. And we come through here. We know that a equals 1 plus b over n. So in this case, we have 1 plus b over n. That means that n is going to multiply the denominator of this expression when we plug it in. So we'll have 2 fn n minus nf, right? So it's 1 plus 2fn n. Yeah. That's what we would expect. So that all looks reasonable to me, but now that I'm looking over here, why do we have these look backwards? Did we label these incorrectly? These are the non-perspective corrected terms, it says, for orthographic. And we've got these two terms in here, but these are the perspective terms. And the ones that say these are the perspective correct terms are not the perspective correct terms at all. I must have done a cut and paste error there, because that actually should be this. So this is actually what we should have been doing for our matrix. Let's just check that again, because that's what's supposed to be there. And we'll see what we get when we multiply through now. Because this is what we actually would expect. So let's take a look at these. We have n and we have f. So test 0 is our near clip plane. Z is -3, W is -3, so that divides out to 1. And we've got, again, exactly the same problem, which is pretty weird. So we've got two totally different equations, and they both end up producing the exact same result in terms of the final divided value, which makes very little sense to me, to say the least. I am correct in thinking that actually did what it was supposed to do, right? Yeah. So these are basically functionally equivalent in terms of the mapping, even with the divide by z, which makes no sense to me whatsoever. I mean, that is just strange, right? Because that sort of is, we derived these two equations, right, thinking that the divide by z wouldn't occur. And so when we did the matrix math for those, we were assuming that the z value itself should come out to, when we plug in the near and far clip plane, we were assuming that the z value itself would come out to be -1 and 1. Here it comes out to -1 and -3, right? Which is totally wrong. And so I'm kind of at a loss to figure out what exactly, were we just doing absolutely horrible math? Like, did we just make absolutely awful mistakes yesterday? Or am I like, am I totally losing my brain here? When we look at this, right, let's see what these terms are. Let's just figure this out here. So here's D and here's E. That's what they equal at the moment, right? And with that D and E, we would expect like it to be evaluating this equation. We would expect D times N plus E, and we would expect D times F plus E, and there you go. And so our matrix is computing what we would expect given those two terms, but they're nothing like what we want them to be, right? So that's pretty bizarre, and I would also like to know why. So let's see what's going on there. If there's, I'm going to start, because I'd like to know completely what's going on here, not just what's wrong with the perspective correct ones. I would like to know the perspective, the non-perspective corrected ones. I'd like to know why those aren't working either. So here's what we typed in, right? And let's just verify that it's what we expected, because we did this math out, right? We said, yeah, here we go. So we did all this math here based on those equations, and we came up with what we typed in here, which is that the D value is 2 over n minus f, right? And the E value is n plus f and minus f. And looking at those two, we should be able to also verify that that's actually what we said it should be here. There's the 2 over n plus f, right? And there's the B value, -1, -2f over n plus f. So did we simplify that down? Oh, we did. This was an erroneous calculation, right? Because I remember that being erroneous. So here, okay, so here we go. 2 over n minus f and n plus f over n minus f. So when did we solve it? We solved for it here. N plus f over n minus f. There we go. So that solution was up here. This is where we worked it out. 2 over n minus f, n plus f over n minus f, right? And that is what we've got there. Yeah. Okay. So here are the two values that we're actually using. And in this case, we know we've got dz plus e is the equation that we're trying to compute. And now we've taken OpenGL out of this. We're just looking at our own matrix multiply, and we did it here as well. So even if we've got a misconception about what OpenGL does, and we could, right? Like these could just be the totally wrong equations to even be writing. And that's fine. But that's a separate part of the debugging. Right now, our math is not even doing what we expected it to do, even just in our own code. So that's an easier thing to debug, and I'm just going to go ahead and look at that first, just to clarify about what I'm thinking about incorrectly here, right? which is to help partition the problem into pieces I can break down. So here's my fz dz plus e, and here are those terms. So that means that f of z should equal 2 over n minus f times z, right, plus n plus f n minus f. That's what I should be computing. I can simplify that z down because in this case, these two denominators are the same. So that's just 2z plus n plus f, n plus f, over n minus f, right? And that's the entirety of the equation that we're looking at. We're just saying 2z plus n plus f over n minus f. N minus f. That's it. So now if I plug in the two values that I'm interested in, if I say f of negative n, what does it equal, right? I would get it's negative 2n plus f over n minus f. Yes? And if I look at what that equals, that's f of negative n equals negative n plus f over n minus f, which, if I pull out the negative here, is n minus f, right? Because that is f minus n, so the negative of that is n minus f, over n minus f, f of negative n should have equaled negative 1. That is what I did erroneously. I was going to say, I'm clearly missing something here because we can't be wrong about all of this all the time. All right. So now let's see if these come out correctly. So here's my test 0. So z over w in this case would equal 1, which again is not right though, because the near clip plane should be mapped to negative 1, if I remember correctly. That's what we said we wanted. And then our f is also 1. So the negative n didn't help. I'm sorry, the negative n negative f didn't help in this case. Which I guess makes sense because, hey, if you pass in the negative in this case, I suppose if we negate both of them, we wouldn't necessarily expect the sign to do what it did. Anyway, so yeah, z over w, and I guess I should say in this case, nope, I'm wrong. We're testing the non-perspective corrected case. So we don't divide. So this is correct. Z is negative 1. We ignore the w because we're testing this branch. The negative 1 to 1 is the mapping we wanted. Okay, phew. Good. So those equations I think are right. They're just not the equations we needed because we need the perspective version of them. Now let's take a look at these equations when using the negative properly and see what they produce, whether we get what we want there. So if I take a look at test 0, I have negative, negative. So this divides out to be 1. Again, not what I wanted. And then test 1 also divides out to be 1 as well. So we don't, this equation seems busted. This equation seems to be working properly. So it looks like we're going to have to figure out where we've gone wrong in our understanding of this. I will go ahead and resubstitute those back in there. But at least now we're actually, we verified that this is correct and working. We just don't actually want to do an orthographic projection here. So that makes it less useful. All right. So let's go ahead and work the other one through. What did I write down here? So in this case, we've got a D and an E. We're looking at the top branch. So in this case, our d value equals 1 plus 2fn over n minus f. Well, I'll be honest, is there a reason that we didn't cross the n's out of this? Like, that's weird that we didn't do that, because this is just n minus f over n minus f plus 2f over n minus f, right? Which is actually a much simpler term. That's n minus f plus 2f over n minus f. Right? I mean, was I hasty there? But that's a crap value. Look at what that turns out to be, right? That's n minus f over n minus f, which is just 1. I mean, there's no way that's right, because that doesn't do anything, right? There's no point to that. It doesn't correct for anything. So we know we must have a sign bug in that term. Like, that's got to be wrong. So I just checked our derivation. Obviously, I'm just as bad at math as I say that I am, because we looked at this and decided that it was still working correctly, but that can't be right. That just can't be right. Because, yeah, look, I mean, there it is, and that's just totally nuts. It even looks like we started to simplify it, and then, like, it must have just been because I was doing this in a hurry. Like, look at this. We started to simplify it, and then must have concluded we couldn't, even though it's obviously simplifiable. I mean, the ends cross even right there. You can see that, even if you didn't pick it up here. That's just dumb. So this is like, yeah, this is some questionable math situations happening here, if we're honest. Just not real good. Yeah, highly questionable. So let's take a look at what's going on there. I'm not sure exactly what's happening with that. So let's just take one more look real close there. We've got the negative a negative b over z thing happening here. We solved for a, and again that looks pretty solid. Because that would be -1 plus, it would be b over, it would be -1 plus a on this side if we moved it over, which would mean that we'd move the negative over, we'd have b over n plus 1, which is what we have. And so that's just what we would plug into the other side, which we did. And yeah. So if we look here and we say that in this case b equals 2fn over n minus f, curious, let's take one more look at this. So if we look at this, we've got 1 equals -1, so that obviously becomes 2, that's right. Negative bn plus bf, that's going to be negative bf plus bn on the top. So that's what we have here as well, which, let me just go ahead and do that out. So 1 equals -1 negative b over n plus bf. That's 2 equals negative bn plus bf, right? That's 2 equals negative bf nf plus bn, oops, and f. or 2 equals bn minus bf over nf. Pulling out the b, you get b n minus f over nf. Oops. Which does appear to solve for 2nf over n minus f. So that b does, I don't know, that looks pretty solid. Just not sure where we're making the bug here. We know we must be, because we're getting it wrong. So let's substitute, well, I guess we can't even substitute back in, because we know this term is garbage. We know the a term is garbage, right? So when we substitute that back in, b over n, we get the 2fn n minus f, and that's divided by n on this side. Make sure I'm doing that right. 1 plus 2fn n minus f. That's crossed n's n minus f over n minus f plus 2f over n minus f. Okay, so wait. Did I get overzealous there? We may be at least slightly okay. N minus f plus 2f over n minus f. That's actually just n plus f. Can't find enough of the math here. Here we go. So that may have just been me being overzealous. Maybe my checking of the math was bad. So what did I do? I said, so here's where we were doing that before. 1 plus 2f n minus f. I said it was n minus f plus 2f over n minus f. That's right. Then I said that was n minus f plus 2f. And then somehow I said that was this. But this was just wrong. So, okay, I'm less nervous about that now. Good. All right. So that does mean that we can treat these like this now. And it looks like we already knew that. In some weird way, right? So this value on the top here is actually not, we do not need to do it this complicated at all, right? It's not, it's just n plus f over n minus f, according to us, which makes that quite a bit simpler. Unfortunately, like I was saying, that's still wrong as far as we know, because the math when we tested it didn't work properly. So now let's actually see what we get. That's actually the e term for the other equation. You look at these are basically the same now, except for the fact that we've got the 2 in the e term is now times f times n, which was not the case before. That's pretty weird, and the term swapped. So I don't know, again, kind of just in math nasty land at this point, but let's go ahead and take a look at those. So here's the d term, n plus f, n minus f, and here's the e term. 2fn n minus f. So our function in this case is going to be the d term times the incoming z value. So we've just got z n plus f over n minus f. And we're adding the e term, so we can just go ahead and add in the 2fn. They're both on the same, they both have the same divisor, right? So let's take a look at our f of z term here. We're going to plug in f of negative n. That's our near clip plane. So if we take a look at here, we get negative n plus f plus 2fn over n minus f. F of negative n equals negative n squared, negative n f plus 2fn over n minus f. Looking at what happens when we keep going with that, we end up with these two terms are both fn terms, whereas this is not. That makes things a little ugly for us. I'm not sure there's much we can do about that. In fact, I can pretty much tell that this is wrong. Oh, no. But we also know that we will be dividing by negative z, right, to get our final answer. So we also know that we will be dividing here, whatever this comes out to, we will be dividing by negative z as well. So we do have an extra n that will appear in the numerator. So that's fine. It's not necessarily fine, but no need to panic quite yet. Right, because this is our equation for the output z value, but the z value gets divided by negative z. So then we end up with this equation. If I write this part out, I get negative squared minus f, fn rather, n squared minus fn. So then I've got an n squared, and in the top, if I combine these two terms, I end up with just the positive fn. So I get negative n squared positive fn. Down at the bottom, I get n squared minus fn, right? That's the same there. And so if I actually look at what this what this should pull out to be, pulling out a negative from this, I end up getting negative n squared minus fn over n squared minus fn, which should be negative 1, right? So when I plug in negative n to this, I would expect to have seen negative 1 coming out of that, right? That's what I would expect after the divide. But if you look at what happens here, I'm not getting that at all, right? I'm getting positive 1 after the divide, unless I'm misunderstanding something. Because w is getting set to negative z, right? Although, no, it isn't. This is my z value, negative 0.1. But it's not getting multiplied by that. Ah! Right. That's awesome. So I guess we see a reason why not to call this UVW, because this is XYZ W here if you add a 4-dimensional vector. This is only a 3-dimensional vector. This W is just this value. So we never actually look at the W coordinate because it doesn't actually come back from this thing. That's bad. Yeah. I'm going to go ahead and say that that's just not going to be... Oh man, I have never had that bug before. I think because I'd never named that W like that before. I don't know why we did that. That's hilarious. Well, that explains why we were having so much trouble with it. Yeah. We're just going to call that like something that's not there, right? Because that's just real bad. That's a really easy mistake for my brain to make. I do not want that happening at all. So basically, like, yeah, you don't get that one. Oh wait, this one's actually okay. This one, it actually is a v4, so that's fine. So it's only the v3 that's just real bad. That's just really, really bad. Let's try that one more time. So now when we look at this, thankfully I'm not seeing that as a W anymore, so that way I'll remember that that's just the UV coordinates. This is a separate way to look at this union. It's unfortunate that there's no way, like, this is one of those things where, like, I wish I could just hint to the debugger in, like, comments that don't show it to me that way, right? I just want to see 3 values, and I want to see them, like, x slash, you know, u slash r or something, right? I don't want to see it as if there's more, because my brain will do something stupid like it just did. All right, so that's actually fine. That's actually just fine. That's going to be the correct value. That's going to be -1, which is exactly what I wanted. Let's see what this one's going to be. This one's going to be 100 divided by -100. Right, this one's going to be -1 divided by -0.1 divided by +0.1, which is going to be -1. This one's going to be +1. Okay. We're okay. That actually looks reasonable, right? So off we go. The only thing I don't know right now, yeah, I guess this is something that that we don't necessarily have to worry about at the immediate moment. But the only thing I don't know right now, and this all looks correct now, so we're back in business. The only thing I'm not sure about is the direction these go. We mapped the near clip plane to -1 and the far clip plane to 1. We're assuming that's correct through OpenGL because that's what we could glean from the spec. But again, since we can't step into the OpenGL code, we don't really know what they're doing. And like it could be that they want them the other way around. So for now, we're just going to have to assume that we got that correct and that that's the direction they go. And I would suspect that we did because we're using the z comparison function that we set up was assuming that that was the correct mapping, and it appears to be working. Although I guess we should, just to double check again that that's true, I should do something in like render group to make upright stuff kind of tilt up like we were doing before, because if I do that, then we can actually see if the z is properly doing occlusion, which we don't necessarily know that it is at the moment. So if I take a look at the push bitmap call here, I'm just going to go ahead and say, you know, if object transform upright, I just want to go ahead and say, okay, let's put the y-axis sort of standing up and verify that that works. So that does again look like the z buffer is working properly there and is sorting in the correct order. And that's all I really wanted to verify, right? You can see if I'm looking from below, I can't see anything that's up higher. If I'm looking from the top, I can see those slanted trees appearing in front of the ground. So all of that is much happier now, and that's good. Okay. All right, so that was basically a case where we actually, ironically, did the math right in both cases and thought we had it wrong because first we had set the near clip plane to the wrong value, which I don't know how that happened. Must have just been a typo. And then second, because I forgot about the fact that W, we had named W to not be for the fourth dimensional element of a V4 in that case. That was just a real bad idea. Now I know. Definitively don't ever do that. I'd never done it before. I'm not sure why we did it here, but we did. And, oops. We could also call it S. I believe S and T are sometimes used for those values. But for now, we'll just leave it unnamed. If we want to name it later, we always can, right? We can always choose to come in here and name it something else. That's not W. I think OpenGL might name them S and T, for example. But yeah. Anyway, now that we've got that under control, quote unquote, we need to go and take a look at how we are doing our sprites, right? So if we take a look at render group here, when we are doing our push bitmap call for a sprite, I'd like to have some idea here about how we're going to make this align with the camera or other things of that nature. So what I want to do is I want to know where the camera is. Obviously, that's important. And then I want to be able to align things to the camera in a sensible way. And we've got to have some kind of technique for doing this, right? We've got to have some kind of an idea about how this is going to work. And so we need to take a look. Let me go ahead over here and make a new entry on the Blackboard for it. Oops. So here's day 365, and I feel like my pen, for some reason, lost its mojo there. Yeah, it did. So, we have to think about sprite cards now. And what I mean by this, we kind of talked about at the end of the stream yesterday, is I want to be able to have my sprites do what it appears to be an orthographic projection, right? So I want my sprites, I want to be able to stand my sprites so that when they're looked at on the screen, you know, even if they're in the corner of the screen, they look like they're standing up rectilinear with respect to the screen, you know? But I want them to do that even inside a perspective projection, where giving them coordinates that looked like that would actually have them look more like that, right? And so what I'm trying to do here is say, let's feed coordinates in which make it appear to be at that sort of angle without it actually being at that angle, right? So even though it's actually going through a perspective transform that does this to things, we put in coordinates that are fake so that it ends up doing that. That's kind of what I would like to do. So if you think about what that implies, if we look at it from the side, what I'm trying to do is say, okay, here's what I've got, right? And I'm looking down at the I'm looking down this way. And so from the camera's perspective, it's doing a transform that's kind of making things on these slices. They're looking correct. If we were to make something at a particular width at this distance, it would look correct if it was in this plane. But we are actually making something that's at this other plane, right? We want it to be this way for other reasons. We want it to be this way because we're trying to make it so that it can stand up in Z. And so what that means is whatever I want that angle to be, and that's something that obviously I can prescribe. Essentially, you can imagine that I have a vector, right? And that vector is the direction along which I am free to move this point. So essentially, once I fix the ground point, you know, so I say that the sprite starts at at wherever it is in z here. What I then have to do is say, well, okay, it's going to stretch upwards, and it's going to stretch upwards at this, along this point, for some distance d. And along that distance, I need it to go far enough such that the projected area into this other plane, right? If I was to look at it this way, and I could imagine that camera plane just being a line going through the ground point as well, and projecting this point onto it, right? In that plane, I need it to be some other height. I need it to be h, which I am specifying to be based on the bitmap, right? So the bitmap is going to prescribe this. I know this vector and this vector, right? And I just want to go as far up as I need to produce this h, okay? And that's the first step. That's only the first step because that won't correct the shear. It will produce the correct height, but it won't correct the shear. So if we take a look here, and you look at what's happening, well, so this is the naive approach, obviously, right? It's just doing nothing in particular. So if you look at what happens here, you can see that I'm getting this sort of, it's making my trees more squat. It's like smushing them. And so I need them to come out to the same size. And as you can, I don't know if you remember from last time, oops. For any given tree, right, I can manually sort of fiddle with this value and get I think that's probably about what it is, right? I don't remember exactly what the tree's aspect ratio should be. But we can fiddle with the value ourselves for any given tree. In this case, I'm looking at this tree right here. We can make that look like the tree should look, right? But the question is, how do we solve that for all trees, no matter how far away they are or anything else, right? Or no matter where they are on the screen. We should be able to produce that value for any tree, okay? And in this case, you can kind of see, too, we're getting that part of the problem there, too, is that z value, whatever it is, I suppose as we get further, I have to think about this. For a camera that's tilted, or I guess even for a camera that's not tilted, where that point is going to matter in terms of the projection down, right? Because when this gets projected, it's going to get projected out from the camera point. So wherever the camera point is, it's going to get projected out onto this vector, right? It's projecting this onto this, right? So I believe, and I could be mistaken, but I believe what we essentially have is we have the camera's up vector, which is the y-axis of the camera in this case, right? So here's the camera. We have some y-axis of the camera. So that's the camera's y-axis. And then somewhere out in the world, we have a point. Here is our ground point, right? This is our P ground. We are looking at this thing. We know that the camera's y-axis is the thing we're interested in down here again. So that's the camera's y-axis, right? And we know that we have another axis, which is whatever the card axis is, whatever the upright axis is. We'll call that U. And we know that that upright axis can have as much of a distance along it as we want. So we can go as far along that as we want, right? So that's our d value. And what we want to do is we want to pick our d value such that when the camera looks at the d value, and projected onto the cy vector, right, we get h. Does that make sense? Hopefully that makes some sense. Now we can produce a number of these things relatively easily. Watch this point, right? Let's think about what these are. So this point here, which is actually the target point that we want, right? This is the place we actually want. So we'll call that point actually P, because that's just the point of interest there. So for that point P, we know that what we've got in this case is P equals PG, oops, plus this D value times U. So we're starting here, right? We're going along U until we hit this P value. If we want to, we can center everything, this entire thing, because both of these are going to be plus PG. We can center everything about PG and just get rid of the term if we want to, right? And we probably should do that. So let's take a look at this, and we'll take a look at this point here. In fact, maybe I'll give these all different P names. So this will be the result P, so this will be P result. And this will be the PY. This will be the thing that's on CY, right? The PY term, that's probably bad actually because I don't really want the Y in there. So let's say this is the P ground term. Oh wait, no, I already used that. P projected. So my projected term is going to be my P ground term plus height, right, times that CY vector. And this is entirely known, right? This whole thing, this value is known completely, right? Because we know the height value, we know the CY, and we know the PG. Those are all inputs. So at the moment, D, right, is the only unknown, right? D and PR are the unknowns. So we know what we're solving for. We're solving for D in this case. And we need to work out the equations in terms of that. OK. So how do we work out the equations in terms of that? We know the third thing that we know, and this is where we're going to get our thing to solve from, is that the camera point, right? So this is PC in this case, camera. We know we have a vector that goes from the camera through this point and down towards the place that we're trying to hit, right? We know that we've got that point. And we don't know the length of this at the moment, I suppose. We don't know the length of that because that's a solve, right? We've got to figure out where these two things hit in some sense, right? We've got to figure out where PP would hit. Now, the interesting thing about that, if we look at it, is we don't really need to know this yet, because we could solve these also in reverse order. We could figure out where this vector hits this vector, right, or this plane, if you will. So we could do a simple ray intersects plane, and we could get this point right here. And once we have this point, then we know this line as well. However, since that's a projection, I don't think that really helps us. It seems like solving for this is just as good, right? Yeah. So here's the way I think we want to approach this, looking at the diagram some more. I think we want to approach this as the intersection of these two lines to get this point. We know this line because it's entirely prescribed, right? We know this point, PP, and we know this point, PC. So PP minus PC, right? And we can even normalize that. This is like the camera ray, right? So we can actually simplify this problem down quite a bit. we can just say that from the camera point, we have a ray, let's say, let's just call that R. We have a ray going from the camera point. We have another ray, in this case, starting from the ground point and going up. We know both of these. That gives us 2 lines. And we just want to know the intersection. Right? That's all we want to know. So we just want to know if we have PC if we've got PC plus T times R, we just want to know, and that's so it's saying somewhere we've got PC, we're going to, in fact, we've done this on Handmade Hero before. This is just 2 lines intersecting. We've got PC plus T R, which is saying I can go as far along this as I want. T is my free parameter of where I go on the line. I want PC plus TR, and I want that to equal, PG plus something times U, right? So T, call that, like, say, S times U, right? And so I want to know where these 2 are going to equal each other. This is actually quite straightforward because this equation is in Y and Z, right? Because I've got Y is this direction. I've got Z is this direction, and Y is this direction. So this, even though it looks like only one equation in 2 unknowns, here and here, is actually 2 equations in 2 unknowns because we have we have Y and Z, right? So all we have to do here is solve for one of them and plug it into the other, and that gives us the solution that we're looking for. So I believe, I don't know that we ever generalized this. I don't think we did, sadly. But we should. Let's take a look. Oh, well, maybe we never really did ray versus ray. Maybe we just did the special case of it being a wall. Yeah, where the walls were rectilinear. All right, so that's okay. That means we didn't waste any work there. So let's solve this for real. So what we want here is ray intersects ray. Right? That's what we're looking for here. Now, you'll notice that in this case, these don't actually need to be normalized. There's nothing in this equation that suggests that these are normalized values, which means we don't even have to normalize R and U first. We can just solve this, and we will get something that no matter what these length of these are, it will still produce the correct solution in terms of those rays, right? Which is also kind of nice. So let's go ahead and do that. If we go ahead and solve this, and I'm going to change these terms around here since we're going to do a generic ray intersection. Let's just call them A and B now. Let's make our diagram much more straightforward. So let's call this like PA and RA, and we'll call this PB and RB, right? And what we're looking for is this point right here. And so what we're looking to do here is do ray intersection kind of a thing. We would be taking a PA-RA and a PB-RB, and we want to output a couple things, like probably a pair of values that's the t, the whatever the t value. So we would want this to output like TA and TB, let's say. which are those multiplier values. So assuming that we have the equation PA plus TARA equals PB plus TBRB, oops. Assuming that that's what we're looking for, assuming that that's what we're talking about, then we should be able to produce the TA and the TB that tells you how far to go along each ray to hit the point where they intersect. So in this case, when we're looking at these values, if we take this and start to solve it for, say, TA, what we would get in this case is, let's go ahead and we'll split this in half. So let's say we solve it for TA. We would get TARA, oops, I want to do it that way. We would get TARA equals PB minus PA, right? Plus TBRB. And then, so we want to solve again for TA. Remember, RA is, as a ray, is actually known. So we would get TA equals PB minus PA plus TBRB over RA. And again, you can't really, unless you're doing geometric algebra, which probably we should, but whatever, you can't really divide by a vector. But that's okay because we're just pretending these are scalar. Like I said, we have two equations, one in y and one in z. So let's just say that we're going to do this one in y. So now we have done all of this in terms of y. So all of these implicitly have a y, right, in them. So this is actually PBY, PAY, RAY, RBY. TB is still just a scalar, right? So we have solved TA in terms of TB. There it is. Pretty straightforward, right? So then we come over here and we just do the x version. Okay? We've got this same equation, but now we want to plug in this ridiculous monstrosity for TA. So we end up with PA plus PBY minus PAY, right? Plus BY over RAY. That's our T value. And all of that is times RA. That, in this case, is going to be the x's. So everybody outside of that is going to be x's because we're going to treat this equation as PAX plus TAX plus PAX plus TA plus times RAX, PB plus PBX plus TB RBX, right? So these are x's. These were all solved in terms of y. So then we're equal over here. We've got our PBX, we've got our TB, and we've got our RBX. Now, again, this we know now to be just in terms of TB. So we only have one more variable. We only have one variable to solve for. So we should be able to solve this even though it's a big, nasty, ridiculous equation with a bunch of terms in it. It doesn't matter because we know we can solve it. We've only got one term left to solve for. So in this case, we again would say, all right, let's simplify this down. PAX up top here. We're going to have, again, we're trying to get kind of this out of there. In fact, I guess what we would do first is probably multiply through by our RAY. So we'd get PAX RAY plus, this term now comes out directly, so it's PBY minus PAY times RAX, right? That's just doing that term here. Plus TB, RBY, RAX, right? So you can see where that's happening, right? The RAY just multiplies through. The RAY comes out on this side as well. So that's PBX ray plus tb rbx ray, right? And hey, now we're basically done, right? There's not a whole lot more to it. We've got our tb terms and they're isolated, so in this case we can combine them. And so we just move all the constant values over to the other side and off we go. So we would have pax ray plus pby minus pay rax minus pbx ray equals tb rbx ray minus rby rax. Oops. There we go. And that's the solution to the equation, right? This just divides out, and you end up with these terms being exactly what they look like. And there might be something we can simplify in there. We've got a pax, pbx, ray. So the ray term in this case, look, you can see that it produces a sort of a simplified version on this side as well. So if we were to simplify these terms a little bit on the top of the numerator, you can see what we would get here. It's ax minus pbx times ray plus pby minus pay times rax, right? That whole thing is divided by rbx ray minus rby rax. And you can kind of see too what this is. This is just the subtraction of the 2 points. So really, you know, if we wanted to simplify this even further, we could talk about this in terms of the delta between these two. Because if you look at this, it's ax minus bx, by minus ay. It's sort of like a flipped version of the negation in both cases. So you could even write it more in terms of this vector as well if you wanted to. But there's not any particularly overriding reason to. So you can see it's somewhat nasty just because there's so much nomenclature in there, but it's really pretty straightforward when you look at it. It's just 2 subtractions with 2 multiplies. You add those together, and then 2 multiplies with a subtraction on the bottom. That's it. We also get interesting information about the structure of the problem here. So you can see if rbx ray minus rby rax, if that's 0, then we can't solve this equation because you can't divide something by 0, right? It's not just an infinity or something like that. It's actually undefined what that is in terms of math we're trying to solve in this case. And that actually corresponds to a pretty straightforward case. It corresponds to the case where like these 2 vectors are parallel or something, right? Because if these 2 vectors are parallel, they'll never hit each other. You know what I'm saying? And you can kind of see how that sort of thing would happen in this case. You need there to be, as far as a dot product is concerned, right? If these 2 vectors are parallel, so let's say I've got 2 2-dimensional vectors and they're parallel, right? So any 2 2-dimensional vectors that are parallel, doesn't matter what direction they're pointing as long as they're pointing in exactly this. It doesn't matter where they are in this case because we're just talking about the vectors. If 2 vectors are parallel, then we know that their dot product is just going to be equal to their length, right? It's just going to be right? We know that this is the fundamental equation for our dot product. We've been over it tons and tons of times. A dot b equals length of A, length of b, cosine theta, right? So we know in this case the cosine theta term is going to be 1. Right? So we know that A transpose B is just going to be equal to length of A, length of B in this case, and the cosine theta term goes away, which is to say that AX times BX plus AY times BY is going to be equal to AX minus BX squared plus AY minus BY squared. Oh, sorry, no, that's not at all what I meant. One step at a time. AX squared plus AY squared, square rooted, times BX squared plus BY squared, square rooted. Right? That's the length of A and the length of B in this case. Right? And we know that there's no cosine term because the cosine theta term will have to be 1 in the case where they are parallel. In this case. Another way to write that would be that, just showing some different equations we could use here to look at the parallel thing. Another way to write that too would be to say, all right, I know that if two things are parallel, you know, I've got a vector and it's, you know, uv or whatever. I'm trying to think of the right way to say this. I've got some vector u, let's say, right? And it goes in a direction. I know that anything that is parallel to u as a vector has to be equal to some value. I'll use lambda for that value. Anything that's parallel to it has to be in the form of this equation, right? It has to be the u vector times some value, right? It can't be anything else because I can't change the direction. All I can do is change the length. So in order for A and B to be parallel, another way to write that would be that A has to be equal to some multiplier times B, right? I know that that has to be true. So that means, in this case, that AX has to be equal to lambda times BX, right? And AY has to be equal to lambda times BY, right? If that makes sense? So that's another thing that we would know about these two things if they were parallel. If that makes sense. So looking at that through here, you can also see that I could substitute these guys in. Don't ask me why I'm going down this. I just felt like kind of having a mathematical aside. I don't know. Maybe we've just been doing too much math, and now I'm in a math zone. But anyway, so you can imagine that this equation is something that would be true about any two vectors that are going to be parallel, because it means that the cosine term for the dot product has to be 1. And then similarly, we would expect this to be true as well, right? We would expect the lambdas to be true. So if I took a look at that a little more closely, that would mean that this would be AX BX would just be lambda AX squared, right? Because we could substitute in lambda AX for BX or vice versa, right? In any case. It's also the case that lambda, right, like either way. We just have to pick one way to go. I suppose that since I wrote it this way, I'll keep going that way. So it's lambda BX squared plus lambda BY squared equals lambda AX squared plus lambda, actually, sorry, that lambda is squared, lambda squared times, because there's a lambda squared now in each of these, lambda squared AX squared plus lambda squared AY squared, AX squared plus AY squared times, I'm sorry, that's a B, BX squared plus BY squared. And if you look at what happens here, we get that situation, that same situation. We pull out the lambda squared, we'd end up with the lambda here, right? And that would go away. And those two would multiply together, and we would end up with lambda bx squared plus by squared, which is exactly what we have on the other side. So this equation just becomes, on both sides, lambda bx squared plus by squared, right? Which is what we would expect for parallel vectors. So down here, we want to know, what are the conditions for which this for which this will end up being 0, right? If we imagine what we would get, how would we get a situation where this could be 0? Well, think about exactly this constraint. If I was to say that I've got my two rays here, because remember, these are our two rays. We've got one ray that's RAX, RAY, one ray that's RBX, RBY. If I was to say the exact same thing about these, right? So I'm going to say exactly this, and to plug it in, then what this term becomes is lambda RBX squared, right? Because I would plug in lambda RB, I'm sorry, that's not right. Lambda RBX RAY is lambda RBY, right? So it would be lambda RBX RBY. In this side, I would get RBY. This RAX becomes a lambda RBX, so the lambda comes out there, RBX. And now you can see that lambda RBX RBY minus lambda RBX RBY, it's the same term. So they cancel and you get a 0, right? So you can see right here that the math, without us even ever knowing it when we wrote it down, has figured out the fact that this problem we asked it to solve is unsolvable in one case, and that case is when these are parallel. And it's pretty cool. I always like how that works out, where it's like, we didn't write any of this ahead of time, right? We didn't tell the math anywhere about any of that. But just the fact that we constructed the problem as we wanted it automatically produced a mathematical operation necessary for its solving that tells us that we have a case we can't solve. So if I didn't know that ahead of time, when I see this come out of the equation, I'm like, oh, oops, like now I know. Better not feed this anything where this term can be 0. And once you start investigating that term, like I did here, you can understand what it means geometrically, and it becomes nice and interesting, right? You're like, oh, I get it now. All right, so that's a little bit of an excessive aside there. I admit that. I'll go ahead and get that out of there so we can see it more clearly. So here's our TB term. And so what remains here is, in the TA case, we would have to solve by plugging in this for TB. We can do that very simply. We've already got TA solved in terms of TB here, so we can just plug whatever the result is that we get. We can just plug it in here and go. So let's go ahead and type that in. Oh, was the game running this whole time? OK. So what we'd like to do here is just make a math function for this. And this math function is just ray intersect 2. We've got a PA and an RA. We've got a PB. I don't really like that being capitalized, but I don't know. Math layout in code is always so unsatisfying. And now we've got our ray intersect call. I need to solve for these two things. So I would like to solve for my TA first, and you can see it's PAX minus PBX, right? I want to multiply that by RAY. Then I want to add PBY minus PAY times RAX, like so. And what I want to do here is I want to do a divide. I want to divide by RBX times RAY. And I want to subtract RBY times RAX, right? So that's my that's my TB value. My TA value is just up here. You can see it. It's PBY minus PAY plus TB times RBY. And that whole thing is over RAY. So that's what we think our equation is in this case. Now you can see we've got a problem here. This is, I believe, correct, although, you know, we obviously could have a math bug there. But the reason we don't want to leave it in this form, although this is correct, is because you can see we've produced another divide here that could be 0, right? So any time that our RA's y component is 0, this would fail. And we know that we've got this condition here of them being parallel being a failure case. We don't want to introduce another failure case just because we didn't plug in the math and follow it through, right? So what we'd like to do is produce a TA that has this worked through that goes with the same denominator if possible, right? So, you know, we've got this over here. I suppose this would help here. I'm using a feature now of Milton that I've never used for this purpose before. I want to write these equations here. So we've got TA equals PBY minus PAY plus TB RBY. I wonder why that drawing doesn't work super well. Like that plus didn't come out at all. TA equals PBY minus PAY plus TB RBY, right? Over RAY. And then we got this one over here. TB equals PAX minus PBX RAY plus PBY minus PAY RAX RBX RAY minus RBY RAX. Right? So if you look at what's going to happen here, if we wanted to plug TB as an actual equation back into TA, right? So we want to put this entire term back into here. Then we can actually, we'll see what's going to happen. RBY is just going to multiply all of these terms, right? If you take a look at what that's going to mean in terms of how this equation is working, you can, let's see, you can imagine sort of what's going to happen here. I've got my TA term equaling, let's see, so what's the best way to work this through? So if I isolate this term first, I would get PBY minus PAY over RAY plus, and then here's this gigantic nasty term, PAX, PBX, RAY plus PBY minus PAY RAX. Those two terms on the top are going to be multiplied by RBY. So we get an RBY in here. Maybe I'll just make that a little cleaner. Get an RBY in here. Plus PBY minus PAY RAX. Oops. RBY. So we have, again, this term, RAX times the RBY in that case. So we get that whole thing times TB. And it's going to be over this situation right here times that. So it's an RAY times RBX RAY minus RBY RAX. And lovely. And by lovely, I mean not at all lovely, for obvious reasons. So yeah, that's not fabulous, to say the least. Looking at the amusement that's going to happen here, assuming I haven't already made a math error, which I probably have, is that I guess the PBY minus PAY term exists in both places. So here's a PBY PAY, right? And here's a PBY PAY. And that might be the thing that allows us to do something useful here in terms of canceling. Because what we want to do is simplify our denominator so that it looks like this again, hopefully, right? Or something close to it. So multiplying these through, what we would get is TA equals this term up here, so PBY minus PAY times RBX RAY minus RBY RAX, right? And then that we're going to add PAX, PB, Y, I believe. You know, this is really problematic. I really need something that's more accurate for drawing because I can't, it's hard for me to see what my terms end up being. And it's easy to make a careless error between the X's and the Y's here because I can't tell the difference between them a lot. Like when I write them, the lag kind of hurts me. Like it wouldn't probably on paper, I suppose. So it's AX minus BX, Y minus Y. So all of the P values are always equivalented, right? So it's PBY minus PAY. Yeah, and I'm really nervous about that. I am almost certain we won't get this math right because of that. I suppose we can go do it on a computer algebra system after this to check what it comes out to be. But yeah, like I had just, it's like when I draw, there's a lot of lag in the switch between those. And so like sometimes it doesn't even pick up the thing. That's just the nature of it at the moment. So anyway, all right. But I'll just kind of finish it through nominally, and then we're going to have to probably go and use something where I can definitely know what the terms are. So I've got PBY minus PAY here. I'm adding, and that multiplies through by this term. we got to have that. We got to have the ray in there, so that's also ray at the head end of it, right? Off by itself. So we've got ray, that whole situation. Then we've got pax, pbx times ray, rby. Oh no, that's not true. Only this part is multiplying that because it already has an ray in the denominator. Ray, rby plus pby minus pay, rax, rby. That whole thing is over ray, rbx, ray minus rby, rax, tb. Right? So looking through this, again, I'm pretty sure we can't actually do this math. I'm pretty sure there's been at least one translation at this point of an x to a y. And probably, I guess, what we could have done is just use totally different terms for all of these to make it easier on ourselves, like an A, B, C, D, E kind of thing. I don't know. It becomes hard when you've got this many things to keep track of them if they're not named in some way that you can actually relate back. But, you know, what are you going to do? So if you take a look at these as they are, we can at least try to do what we would do and have some semblance of that here. So if we take a look at what happens in terms of pulling out terms, we've got a by, pay subtraction term here. So that actually groups together, and we would end up with a single term here that was rbx, ray, rbx, rax, plus the rax, rby term. And so we can go ahead and do that one. This would be pby minus pay is this term. We've got, that's just an addition in there. So we know we've got rbx, ray minus rby, rax, plus rax, rby. And these two terms, therefore, would cancel. You can see this is an rax, rby in both cases, right? So we end up with only that. We then add this term, which is pax, pbx, ray, rby. What we're looking to do is cancel the rai, and now we've found ourselves in a good position. There's an ray and an ray in both terms. So those all cancel, and we are left only with pby minus pay, right, times rbx and pax, pbx times rby. But that's a minus. That should have been a minus there, right? That should have been a minus, right? It's this term. I highly recommend, if you're doing math, folks, do it on actual paper. Because it's real hard doing it this way, let me tell you. So that's the actual term now. How did we still end up with a TB in there? That was dumb. That's incorrect. Right? There's no TB. We substituted TB in. Right? So that's what that actually looks like. So looking at that, right, if we take a look at it, they're pretty much exactly symmetric. So rather than solving it that way, which introduces a synthetic divide by 0 we don't need to worry about, we can instead solve it this way with the math worked through, which is pby minus pay times rbx plus pax minus pbx times rby, right? And these are in terms of the same denominator, which is exactly what we wanted. So I'm going to call this denominator d for denominator. And now we get to the actual equation. And you can kind of see here what we can do is say, all right, let's compute that denominator. If the denominator is 0, then they don't have a solution, so we're not going to be able to return anything to you. But if it's non-zero, then we can go ahead and do it. Now, this is not super numerically stable because as this approaches 0, we will get really huge values. So in general, this ray intersection routine is not meant for people doing anything wild, right? It's only really meant for people doing something sane. And that's fine, because we know when we're using it, and that's OK. If we ever need to use something wild, we need to think through the math in a different way and take into account whatever the special things are in the case of that, whatever that thing is that we're doing. So if we look here, we can see sort of our two values for TB and TA. I'll go ahead and get rid of that. You can see here our value for TA is the by minus the ay and the ax minus the bx multiplied by the two rbx, rby's. And it's almost a symmetric equation in the other case, the pax minus the pbx times the ray, pby minus pay times prx, and both divided by this product here, which again talks about the parallel nature of the two rays. In this case, like I said, that was pretty hard to read writing it on the blackboard, and so I don't really know that we were able to get that math right. I don't have a CAS installed on this machine, but we could, if we want to, try to get Wolfram Alpha to check our stuff for us. I don't really remember the syntax for Wolfram Alpha. I think it's similar to Mathematica, but I don't really remember. So here's an example. Apparently, we can just do the two equations separated by a comma. In this case, we know what those two equations are, right? Oops, just my pen. This is what we want. So in this case, we have PAX plus TA. Does it know? It's not going to think those are all different variables, does it? Is it? Does it? Well, we'll try. So if PAX plus TA times RAX equals PBX plus TB times RBX. And then I have the exact same thing, but in Y. Okay, well, ladies and gentlemen, the knowledge engine. Can I get it to know that it's a solve somehow? Okay, that's fine. I don't know how to get it to solve these things for us. I would like it to solve a system of equation. It did here. I don't know how it knew that that was a system of equations and that my other one wasn't. How do I tell it what to solve for? Because I'm not telling it what to solve for. For. There we go. For TA. I give up. Solve system of equations. Stephen Wolfram, what is the deal? This is pretty simple, folks. I just want to check my math. And this is like the most simple thing. This is like the most basic thing I could possibly ask you to do. I just want a computer to check my math for 2 equations and 2 unknowns. I mean, right? I mean, those are the equations, but again, I don't know how to, I don't know how to make any of these things know what's a constant and what's not a constant, right? Because this is a symbolic solve I'm asking it to do. I don't want it to solve for numbers. Like, I'm not asking it to solve a numerical equation. But I give up. Who knows? Maybe we'll never know. Anyway, that is the math as we worked it out. There's our 2-dimensional ray intersection case. You provide the 2 rays, and it does the intersection call. It produces the intersection back, which I'm just going to say for now is right. Someday we'll find something that can check our math for us. How this isn't just built into an editor these days, I have no idea. Computer programming is so ridiculous. It's like it hasn't changed in 40 years, and somehow we still are at a situation where I can't even check basic math without buying a $1,500 piece of software, apparently. Anyway, grumpiness aside, here's our ray intersect 2. Let's just assume it's right for now because we can fix it later when we can actually check the math somehow. And we'll just look at how will we use it if we knew it was correct. So assuming that we have an upright transform, we have exactly the situation that I was talking about before. We know exactly what our construction is because I described it previously. And so we've got our basic point that we're passing down. That basic point that we're passing down is this entity P right here. We know the camera transform because that's something that's set in the render group. So we can extract the axis of that transform if we want to and use that as that other value we were talking about. But for now, we just need one other thing that we have not specified, and that is the card, whatever that card axis is. And I don't know what that card axis should necessarily be yet. Let's say, for sake of argument, that card, that standing up angle, I don't know what that is exactly, but this is the card. The card is going to be something in YZ, right? We'll call this card YZ going up. And that vector is just going to be something like, I don't know, probably going maybe 25 in Y and 75 in Z. Like the cards probably should be fairly upright. They shouldn't go too far in Y. I don't know, but maybe not. It could be 0.5, 0.5, something like that. This is non-normalized at the moment, but we don't need it to be normalized. Like I said, we solved for the intersection not expecting anything to be normalized, so that should be fine. So we have the card xy. That's what that vector is, one of our vectors. The other vector that we need to know is the one along the ground. So we need another piece of information, which is the camera yz vector. We don't know what that is yet, so we have to extract that out of the other transform. But now we know everything else. I guess we also need to know the cam p. So this is the cam p yz. I guess we'll do it this way. This is the card ray, camera ray, and the car p yz is just going to be entry p yz. And that's everything that we would need to solve this equation. So we just need to extract these two out, right? But otherwise, when we call the ray intersect code, this would give us the intersect point. That we were looking for between the two rays. So the cam p yz, cam ryz, this is the card ryz, sorry, card p yz, card ryz. This would give us the intersection point. So if we take a look at what that's giving us on the diagram, that intersection point is the distance along the ray we would go to find the point that we're talking about. And so in this case, we already know the y-axis is going to be this axis. So we actually already kind of know what this is going to be, right? We sort of are getting an input from the user, which is trying to rotate that. And we're going to have to take that into account separately in terms of when we want to start allowing that, that shear to occur, which I guess I hadn't thought about too much in this case. So we may have to kind of go back that in a little bit more later. But for now, what we're trying to do when we get this ray information out is the distance from along the camera to get to it is going to be here. The distance from the point along card ryz is going to be our TB value, right? So the thing that comes out in y, right, that is actually going to be the value that we need to go along. That's how long our y-axis needs to be, basically. So, you know, in this case, we've got the size y. Yeah, we've got our size y, and that's going to come into play when we compute these two things. And we've got our y-axis computation, which now is going to be down here. And that's going to be this. Unfortunately, this we need to sort of put a to-do in here. Because right now we're sort of just going to be doing this, right? We're going to be assuming we're going to get the size right, but we wouldn't handle the rotation right yet in terms of correcting this card. So when we get the camera p yz and the camera ryz here, then we'll be good to go. So let's see how we would get those out. In terms of our render group, we know that we have our projection matrix, which is the one that we're using at the moment. And that projection matrix actually has the information that we want. So if we want the y and z locations of the camera, we could back them out from here. But what I would prefer to do is actually not have to do that every time we want to look at them. So I would rather have something which basically just stores this info for us, because when we want to do computations with them, it's nice to be able to grab that out. And we can do that very easily because we know when they're set. So what I'd like to do is say, all right, if we want to get the camera P YZ, we should be able to get that directly out of the group. So the camera P Y and the camera P Z is exactly that. And I guess I can just do it this way. So the only confusing thing is how do we get camera R Y Z? And in order to get that ray, we need to figure out that kind of offset along the camera's y-axis, right? Remember, way back when we started the math, we drew this, and we said, well, wherever the entity's point is, there's the camera's y-axis. It needs to go out that much height, right, along that axis. So we need to say that the camera's RYZ is going to be whatever the camera's position is, right? We're going to subtract that away, and we're going to have the entity's placement, wherever it is, plus the height, which is that size y, times whatever that camera y-axis is, because that's what we're moving along, right? And this will give us that camera vector that's pointing down. So that's actually all the code, right? That actually does everything we want it to do in this case. There's nothing more to it. And then, you know, we obviously want to predicate this because we don't actually want to do this operation if we're not talking about one of those sprites that's supposed to kind of be standing upright. So if we take a look at what's supposed to be happening here, and we just look at this, we're like, okay, this is the math that we're talking about that we worked out. Again, we probably have a bunch of bugs in there. We don't even know if this routine is correct yet because we can't check it at the moment, and we need to check it. But what we can do is finish off this before the end of the day. We can go down here to when we actually set our camera transforms. When we set our camera transforms, we can take those camera X and Y's and actually use those to set up what we actually want to do. So in here, when we do our set camera transform, I want to take a look at who is calling that at the moment. And that's all fine. And that's all fine. So if we want to, I think the way I'd like to do this, because this is already known, I think I'd like to do something like this, which I think is how we had it before, but I feel like we maybe want to do that because I want to store this information, and I'd rather not have people have to back it out. So it kind of feels to me like maybe that would be the best way to do it. So, you know, in here when we've got world mode, instead of calling the camera transform code, maybe we just we force you to pass those in here instead, because we want them to be stored. Because they're things we're going to need to do computation on. We could back them out from here, but then we're doing a bunch of math for no reason because we already had that information, if that makes sense. So that kind of feels like probably a good idea there. So maybe I'll do this. And then inside render group, I'll do something like this. And that's the way we had it before, and I figured, well, it was easier to pass in a matrix, but in this case, I do kind of feel like it is it's a little more interesting to do it this way, because then I can save those values, which is what I want. And in this case, that makes this a little bit more of a pain, but only a little. And in fact, now that I think about it, we could just do something like this. And off we go. That is not nearly as messed up as I was expecting it to be, given how little we had testing-wise there. But you can see we've still got some nastiness here, right? Right, you can kind of see we've got a little bit wrong in our it's not completely wrong, but it's pretty close. So yeah, so you know we're not too far off. I'm going to stop there because we're going to have to go dig into that math. And like I said, it should be pretty easy to check the work, but that's okay. And like I said, it's really hard. I did not do it on paper there. Those terms all look the same. The drawing is just not high fidelity enough. It's kind of laggy, and it has a lot of noise in it. And it's really hard to do. My handwriting isn't that great to begin with, so it can't really handle that extra suffering. But we will check it out. So if there are any cute questions for now, I can take them. If not, we will deal with it next weekend, finishing the debugging there, and then we should be good to go. Games, there was a lot of chat about Wolfram expecting one-letter variable names and interpreting RBX as R times B times X. Yeah, I was wondering if it would do that. I don't know. Bill D. Strong, didn't we do this math when doing the screen projection? We might have. I don't remember. We didn't pull it out into a function if we did, though. Miblo asked, do you think we need an epilepsy warning there? I don't know. I don't know what doesn't trigger epilepsy. Pepe fell. Hello, yesterday I was asking about shaders and the Z buffer. Could I rephrase the question? It will be the last time. Sure. Masfielda, maybe if you swap the order of the sum on TB, you get an equation more similar to TA. They're already pretty similar. You're just talking about getting the y's lined up. Something like that. Can we show again the equation? Yes. So the equation is in these terms, right? It is that we want PAX plus TA times RAX to equal PBX plus TB times RBX. And at the same time, Y. So we're saying a base point, PA, plus some scalar times the ray direction A equals some base point B plus some scalar times the ray direction B, right? And that's all we want is just, it's literally just A plus BC equals D plus EF in X and Y, right? Is the stream weekends only now? Yes, the stream is weekends only now. "1935 is Molly Rocket's upcoming volitional fiction game." Oh, Insobot actually knows that. That's cool. Pepe Val, as Handmade Hero is a 2D game, my idea would be to treat the Z variable not as the Z coordinate, but as a variable that the pixel shader will use to kill hidden pixels and do alpha blending with the GPU power. Well, so the first part is like, well, the Z value is, that is what the Z value is. So we are doing exactly that, but if the Z coordinate is, we want it to be where the thing is in 3D. That's what gives us the depth sorting that we want. Alpha blending, on the other hand, you would have to say, how do you think the alpha blending will work, right? Because the only way to do alpha blending is to have a sorted order of combinations of the things that you're passing down. And so there really is no way to use the Z buffer for that unless you do, like I talked about a while back, something which actually uses frame buffer atomics to keep a list of all the things you do and then resolve them at the end, right? Let's see. Any other questions about what we're doing? Doesn't look like there are any other questions about the code. Just to ask the person who wanted to know about seeing the equations again, did this do that? Was this what you wanted to know in terms of what the equations are? Macielda, are you doing this so you can mix perspective projection and orthographic projection for game objects? Yes. Basically, it's so that I don't have to... it's so that if I want to, I can just always think of everything in the same world space and not have to think about everything as maybe going through two different matrix paths and having to line up and stuff like that. So I was kind of hoping I could figure out a good way here to just output sprite cards that do whatever we want, and we can keep them all in the same space. Rooktag, now we have the alpha issue with the 3D stuff. Is that easier to fix than the 2D sort because you already know how to fix that? It's not necessarily easier to fix. It's just that going through the Z-buffer path, we are guaranteed that we can scale properly because we know that we can basically treat the edge alpha as something that can be solved via, for example, alpha to coverage and a multi-sample buffer if we want to. Or maybe there's other good techniques we can employ for that, just the little edge alpha. And then for shadows and stuff like that, we probably won't have to sort those. We can probably just break them into two groups, things that are shadow-like and things that aren't, and draw them in two passes. So I think we should be able to get away with not having to do inter-object sorting pretty much at all. For the most part, and that's really what I wanted to get away from. So it's not like it's still completely trivial. It's just, it's something that'll scale better because I want to be able to have lots of sprites on the screen, and I don't want to have to constantly worry, if that makes sense. I don't want to constantly worry about the sort being a bottleneck, because there's lots of things we can do per pixel to try stuff on the GPU, and there's not a lot we can do to speed up the sorting. When lots of sprites are overlapping, it's just sort, and sort is bad. Sort's n squared, worst case. In a lot of these algorithms, it's n log n, even if you do it most optimally. Somebody ran the equation through MATLAB, which is what I wanted to check. It says this could be the solution at least for MATLAB. Negative PAX RBY, negative PAY RBX, negative PBX RBY, plus PBY times RBX over. So the denominator is the same. The numerator is at least slightly different. Let's take a look. I'd like to take a look while we're here just to see. Good, so people plug this into some math software, which is what I want to do. So I would like to check this work. Let's take a look here. So we have PAX. I'm looking at the one from Derive 6 here. We have PAX RBY, which is what we expect, minus PAY times RBX. So So it looks like it multiplied this out. Let me go ahead and multiply this out just so we can see a little bit easier what we have here. So we have PAX RBY minus PBX RBY plus PBY RBX minus PAY RBX over D. And the equation here, they're both over RAY RBX minus RAX RBY, which is what we had, right? Although they've got it the other way around. So we have RAY times RBX, oh no, times minus RAX RBY. So they've got the same denominator in both cases, which is what we've got, right? The denominators match up. So that's good. And then in the TA case, PAX RBY, that's what we've got here, minus PAY RBX, PAY RBX what we got here, minus PBX RBY plus PBY RBX. So that looks like the same thing. TB is PAX RAY, PBX RAY, PAY RAX, PAY REX, and it's a negative. Then a negative PBX RAY and a positive PBY times RAX. A positive PBY. So it looks like we got it right. So it looks like that's correct. Shockingly. So that's good. All right, so our ray intersection math might be good. And that's good because that would mean that all we have to do is just take a look at our usage of it a little more closely and make sure that we're doing everything correctly. This part right here obviously is kind of hastily thrown together that I was just putting in there, but you know, this thing about grabbing out the camera position and taking the the RYZ, which is the entry's sort of ground point, plus the camera's y-axis, how far we wanted it to go, how far we wanted it to appear along that y-axis, and then we took from there and subtracted away the camera's location to get the vector kind of going towards that ground point. And then we kind of made up the card poking axis there. Does that make sense? Oh. Well, this is just totally bogus is why. We never really finished this out, did we? So we were supposed to use this as the card YZ, first of all. That's what we actually were supposed to put there. So technically, we weren't doing that at all. That's pretty weird. So actually, we're surprisingly good so far. Our lower set of trees is not correct, but our upper set is basically exactly right, it looks like. That's exactly what I wanted there. You can see it's keeping this guy quite right. So we're not correcting, you know, we haven't tried correcting the shear yet, but that's quite good, actually. Yeah. I'm very happy with that. All right. But we still have some issues here on the, in terms of getting these guys to line up, which might, you know, we also do sort of have the issue, I don't think this is that issue though, but we do also have the issue of the parallel lines as well, obviously, so there is that issue, but that's actually pretty good. So we're in pretty good shape there. So that's good. And Macielda said it seems that Valbus's solution is negated in relation to yours. Negated in the whole, meaning the whole thing is negated like that. Let me see what Valbus's is. Yeah, it does look like yours are negated, but why? So why the other one is not negated? How did we get two computer algebra programs to produce two different results? Because did you guys look at the one that that Pepival posted there from Derive? Do we know which one of those is correct? Because it doesn't look like, I mean, you shouldn't be able to negate them both or not negate them both, right? You should have to do one or the other is the correct answer. And so I'm wondering, since I haven't done it through the computer algebra system, I'm wondering why Derive 6, did someone enter it in a weird way? Like why, or did I check it wrong? You know what I'm saying? Because I don't think, it can't be both. And I'm pretty sure that I checked it correctly versus, yeah. So I'm pretty sure it's not negated in that sense. But we'll have to see. And I think that looks pretty right to me too. I feel like we're correct here. But I could be wrong about that. And also, that's very stable. Like, this is looking quite good. It's just as we flip around through one part of the projection, we get a bogus answer through there. But like, look at how stable that is everywhere else, right? We just have a singularity there, which may be the parallel projection part of things. We'll have to take a look at it. But you can see that it's very stable for everywhere else, right? Like, it's doing exactly the correct sprite thing everywhere else. It's worth noting, too, that we can always do sort of a separate thing, which is that one easy sprite thing to do, and it's not necessarily the sprite thing that I want to do, but in addition to this, we also have another option here, which is that you know, the entry x-axis equals size x times group camera x camera y. And so if you want just regular sprite cards, you can do that as well, right? So you can see it's very easy to just produce a standard sprite card, but that's not necessarily what we want to do here, right? The reason for that is standard sprite cards don't stand up properly if you're looking down at a steep angle, right? They're tilted in kind of in a not sufficient way potentially. It might be that that's still fine, and we'll have to play with it. But I wanted to have the ability to do something a little fancier there potentially. So we'll play with it a little more. But you can see that if we wanted to do something like this, we could just leave it like that, and that would be fine, right? Because you can see that what we're getting here is now really our only problem is with shadows, right? That the alpha, our alpha stuff is bad, right? if we were to clip out everything that had alpha in it by setting the alpha func to get rid of it, then you can kind of see we pretty much have no problems at all at that point, right? But unfortunately, that you know what? I've never done that test before. You can see that our sprites don't have perfect alpha everywhere, right? Those must have like 254, 253 alphas or whatever. But you can see that we don't have any of those problems anymore, and really the only thing we would have to fix is just a couple, like our rectangles are drawing right on top of each other, so you get the Z fighting. But other than that, we don't have any problems, right? Our sorting is all now perfect, and everything's good, right? So really, we just need to, again, figure out sort of roughly what our solution to the other problem is going to be and how we're going to handle that alpha, because at the moment, we don't have any solution at all for the alpha. I wonder if it would be sufficient to just the game just works like that. I wonder. Without doing anything else, you just do it that way. I wonder if the sorting works properly. Because it works pretty well, right? If we went ahead and solved the alpha problem, which we have to do either way, maybe that's just sufficient. I don't know. It's an interesting question because I guess you really don't need, you just need only the tiniest amount of Z overlap. So if you just tilt the camera just a little bit, you know, I don't know, maybe that's sufficient. It's an interesting question. It's an interesting question. All right, anyway, we'll take a look at this next week. And basically what we're trying to do now is just, again, kind of converge on a good solution for how we're going to do those sprites. And then we can move on to dealing with our alpha. Because that's really the only visual artifact problem that we'll have once we get the sprites lined up however we want them to be. We just have to figure out what a good solution would be for our alpha compositing. And that might involve doing like something like alpha to coverage. It might involve doing something else. I don't know. So we'll have to think a little bit about that and think about how we want to solve that problem. Because again, that is the one translucent or transparent objects are the things that rasterizer pipelines have the very hardest time with because of that reliance on the Z buffer. That's just how it goes. So that's the thing. We get everything else for free. We don't have to do the sort anymore. Everything else is nice and clean through the entire pipeline, but you still run into that nasty bit of how you're going to deal with transparency and translucency. So that's the one thing we're going to have to address. All right, I'm going to go ahead and close it down. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can play around with it. We also have the forums you can go to ask questions, a Patreon page you can go to support the video series, schedule a bot that tweets the schedule at you, and an episode guide where you can go to catch up on old episodes. That's about it for this week. I will be back next week, same time probably, but check the tweet bot if you want to know for sure. Until then, have fun programming, and I'll see you on the internet. Take it easy, everybody.